Here's my pointer. Let me turn this guy off. So there we are. You can find me in this building. The email address is evans@berkeley.edu if you need any further information. And my collaborators in this topic that I'm going to talk about today are Mike Schneider, who graduated with a master's degree from mechanical engineering about a year ago, and Professor Paul Wright from mechanical engineering, who most of you know. Three other people have gotten involved in this project recently. They are Dan Steingart, here in the audience, so you can correct me when I make my mistakes. Andrew Redfern, who is also here, and Nate Ota. I'm not sure that Nate's here. Anyway, this research has been supported by the UC Energy Institute and by Honeywell. And here's the outline of my talk. First off, I want to tell you about the significance of industry, particularly with regard to energy consumption, and particularly regard to energy consumption in the production of aluminum. I want to describe to you why we think wireless instrumentation is important for work on for the production of aluminum, for monitoring the production of aluminum. I want to tell you about some work we've done at an aluminum plant called East Alco, which is just outside Baltimore, including a campaign which is very successful in April of last year. Tell you what we've concluded from the work so far, and finish off by talking about other industries to which we can apply this technology. So let's start with some statistics from the Energy Information Administration, which is an interesting organization, a federal government agency which provides all kinds of interesting statistics on energy. And they tell us that in the year 2002, there was a production of 70.8 quads of energy in the United States. A quad is 10 to the 12 BTU. So that's a large amount of energy. And what fraction of that energy was consumed in manufacturing? Well, you have that number down here. And that my pointer is not behaving itself. So of this 70.8 quads, 22.7 quads was used in manufacturing. Manufacturing of automobiles, aircraft, drugs, food, all kinds of things. And of that 22.7 quads, 832 trillion kilowatt hours was the amount that was electricity. So that's a large amount of electricity. And if I look at that, what fraction of that electricity was consumed by the primary aluminum industry, it turns out to be 56.7 trillion kilowatt hours. Now, I should explain two things here. One is, what is the primary aluminum industry? That's making aluminum from ore rather than from recycled metal. And what's the significance of this number? Well, I want you to think about what you pay for electricity in your home. Now, that depends upon things like where your home is located and whether you have gas as well as electricity and how much you consume. But a round figure might be something like 10 cents per kilowatt hour. So if you had to pay this electricity bill, you'd be paying about $5 or $6 trillion per year for electricity, for producing aluminum. Now, in fact, it's not as expensive as that to the aluminum industry. So a representative number might be around 2 cents per kilowatt hour. But you can see that's $1 trillion that the aluminum industry in the US spends each year on the electrical energy needed to produce aluminum. So it's a significant business. It's not anything small. So what's the good news with regard to aluminum? Well, first off, the aluminum industry makes a big deal out of the fact that if you use a significant amount of aluminum in automobiles, you have all kinds of environmental benefits, right? You significantly improve the gas mileage because you reduce the vehicle weight compared to making those parts out of steel. That means lower CO2 emissions, so that's good news. Another thing the aluminum industry does is crow about the success of beverage can recycling. So I hear somebody opening a beverage can right now. The probability of that beverage can being recycled to make aluminum is about 2 in 3. Right? So about 2/3 of the aluminum produced in this country and used as beverage cans gets recycled. So that's good news too. I think there's very few other materials that can claim that success. Another success, if you use aluminum, for example, in window frames rather than wood, this obviously conserves forests, which is something we'd all like to do, no doubt. That's the good news. Now to the bad news. You've heard some of this bad news already. There's a lot of electrical energy used in the production of aluminum. In fact, an interesting statistic is that there is now more electrical energy used in producing aluminum than is used by the whole of France. So it's quite significant. So think energy consumption when you think aluminum production. Another thing you should think of is emissions, because the production of aluminum entails the emission of significant amounts of greenhouse gases. So for every ton of aluminum we produce 1.25 tons of carbon dioxide. And worse than that is we also emit fluorides in the production of aluminum. In fact, those fluorides are fluorinated carbons, PFCs as they're known, and they are between 1,000 and 10,000 times worse than carbon dioxide when it comes to global warming. So if we translate the amount of PFCs, which is quite small in tonnage quantities, if we apply that factor of 1,000 to 10,000 to it, then we wind up with 50 million tons equivalents of CO2 that are ascribed to the fluorides which are emitted in producing aluminum. So think energy consumption and think of emissions, particularly fluoride emissions, when we talk about aluminum production. Where is the aluminum industry? Well, the US is still a major producer of aluminum, along with Canada. Russia is another producer, China and Norway. Now, about 5 or 6 years ago, I counted the number of smelters in the United States, and there were 23 at that stage, and they're now down to about 12. Here's some statistics from the International Aluminium Institute, which is located in London, hence the pronunciation and spelling. So I'm sorry that this graph is not very visible at the back. This is primary aluminum production in thousands of metric tons. And you can see North America, US and Canada is quite substantial, reducing somewhat over this time period from 1998 to 2004. All the rest are increasing, you'll notice. This Western Europe is primarily Norway. Asia is China. China's aluminum industry is increasing its production quite rapidly, as is Latin America. Latin America, primarily Brazil and Venezuela. So we're still big makers of aluminum in this country, although there's been a decrease in production over the past few years. So this is an interesting little table, in my opinion. There's this. Start off with this column here. This is the amount of electrical energy involved in producing a ton of aluminum. So it's about the same in every country. Somewhere between, here's the low, 14.7 megawatt hours per ton of aluminum in France. Where's the high gone? Norway, I think, isn't it? Yes, it is. 16.6 megawatt hours per ton. So in terms of how much energy it takes to produce a ton of aluminum, there's not much variation from country to country. But now look at the price of electrical energy in these countries. And these are prices as charged to the aluminum industry through things like long-term contracts. And these are rather dated figures. These numbers come from the 90s, but really not much has changed there that you need to know about. But look at the variation. The United States, 2 cents per kilowatt hour, compared to Canada at 1.05 cents per kilowatt hour. So you can see that there will be considerable incentive to produce your aluminum in Canada rather than in the United States. And you'd be absolutely insane if you tried to produce it in Spain, right? Might not be too bad to go to Venezuela, right? So that spread in the cost of electrical energy is driving a lot of change in the aluminum industry. So one of the changes, of course, is reduction in electrical energy. These electrical energy consumptions per kilogram of aluminum, sorry to bounce around between units here, but the important thing is if we look at over the last century, the amount of kilowatt hours per kilogram of aluminum has dropped by a substantial fraction to something of the order of about 16 kilowatt hours per kilogram of aluminum. So that sounds like a nice reduction. That's a success, right? But in fact, this number is about 2.5 times what you need, 2 to 2.5 times what you need theoretically. Right? So of the electrical energy that goes into the production of aluminum, something like 55% is wasted It's not involved in actually producing the aluminum, but in producing heat, which is subsequently wasted. What's the technology look like? This is a cross-section of something called a Hall cell, or a Hall Hérault cell, if you happen to be more of an international bent. Hérault is a Frenchman who invented this technology at the same time as the American Charles Hall. These things are big. So from here to here is about 10 feet, let's say. It's about 15 feet high, and in the direction perpendicular to the screen is something of the order of about 40 feet. Let me point out the principal features. There are carbon anodes in here, and they are connected to this superstructure here, and current flows down through these carbon anodes. DC current, of course. It flows out of those anodes and into a molten salt electrolyte, which sits in this region here. That's at about 960 degrees Celsius. And below that is a pool of molten aluminum, same temperature. And below that, a carbon lining, so the current flows down through the anodes, through the molten salt electrolyte, through the metal, into the carbon lining, and out through these things called collector bars in the bottom of the cell. And then it goes on to the next cell. So several cells is strung around in series. I want to finish off by pointing out these panels at the side here. They're called fume shields in this diagram, but various companies have different names for them. More common to call them panels, cover panels, something like that. So that gives you some idea of the technology, but a better idea is given by this photograph here, which is a photograph of an actual smelter. I think this is an Alcoa smelter. So this is one of these cells. This is another of these cells. This is another one. You can see they stretch off to infinity. Right? So a typical plant would have 300 or 400 of these cells. The current that flows through these things is enormous. So through each cell, you put something between 100 and 500,000 amperes. Right? Alcoa is building a new plant in Iceland where the cells are 400,000 amperes, and there are some experimental cells operating at 500,000 amperes. Not very much voltage across them, only about 4 volts, but enormous currents, which in fact generate enormous magnetic fields, which is significant to what we've been doing. Come back to some details here. This is a cell superstructure. This is just here is the rod from which each of these carbon anodes is suspended, and there typically be about 10 or 20 along each side of the cell. These are aluminum bus bars which bring this enormous current to the cell from the upstream cell. So the current is flowing in this direction all along this pot line. There are substantial electrical hazards associated with this, so that if there's a 4-volt drop across each of these cells, somewhere along this line of cells, there's going to be a voltage difference of several hundred volts between the pots and ground. So there are electrical hazards. And those electrical hazards result in it being very difficult to run wires around in this operation. So there are now no power sockets anywhere near these cells to prevent the possibility of maintenance people making connections through the power circuits. This, incidentally, is a ladle which is presently being used to siphon aluminum out of this particular cell. These are the cell covers I pointed out earlier, and they're significant to this investigation. These are 2 normal-sized human beings. As opposed to dwarfs, as I know. Okay, so they're about the size of a shipping container, contain molten fluorides at this temperature. I've told you about the flow of current. The significant point here is the only instrumentation on these things is a voltage measurement. Right? So these huge beasts, which have this enormous current flowing through them, and they're sitting at 960 degrees Celsius, the only measurement the operators have to work with is a voltage measurement. Now, these things are quite expensive, as you can imagine. I think if you took 3 or 4 of them, 3 or 4 cells, you'd have the cost there of a small commercial airliner, right? And think of the instrumentation on a commercial airliner compared to the instrumentation on this guy. I tell people this technology is like trying to fly a 747 with the instrumentation of a Sopwith Camel, with an altimeter and an airspeed indicator. So there's a great need here for some improved instrumentation, and that's part of what the technology is about that I'm talking about. So I want to come back to emissions for a moment. remember these molten fluorides in this cell at 960 degrees Celsius. One source of emissions from the cell, fluoride emissions, is a contact between air and the molten fluoride, because air typically contains water vapor that reacts to the molten fluoride, produces hydrogen fluoride, which escapes from the top surface of the cell. And that fluoride generation is minimized by maintaining a frozen crust on the top of the salt. So if you look inside these cells, you don't see molten fluorides. What you see is what's known as an ore cover. It's whitish in color, and it's mostly frozen electrolyte with some of the aluminum oxide, which is fed to the cells, scattered across the top. And one of the responsibilities of the operator is to maintain that frozen crust, sort of like a pie crust on the top of a pie. And if it develops any holes for any reason, the operator is supposed to go in there and scrape the alumina around and cover that hole so as to avoid this contact between air and the molten fluoride electrolyte. Another good way of minimizing the fluoride emissions is keeping these panels in place that I pointed out to you. Those panels are there so that the gases which are generated in the cell are sucked off the cell through some ducts, which I failed to point out to you, but I will go back to. So over at this side of the cell are these ducts leading into this big duct here, which is under vacuum or reduced pressure, so it sucks the gases into a gas cleaning system. So if you keep the panels in place, the emissions get sucked into the gas cleaning system rather than escaping into the pot room. That's the name for these big buildings which house these things, and therefore exposing the operator to fluorides and allowing fluorides to escape from the building. Now, both these things, maintaining frozen crust on the top of the salt and maintaining the panels in place, are made difficult by the need to replace and adjust these anodes. These anodes are consumed by the reaction, and periodically you have to go in and replace them. And even more frequently, you have to adjust them downwards as they are oxidized away. So there's a tension here between what the operators have to do and what you should be doing to maintain low levels of emissions. So this brings us to the application of wireless technology. So we're going to instrument these cells to improve things, and in the recent work we've been doing, it's been aimed at improving emissions of fluorides. So these cells are ideal for test cases because they have very limited instrumentation at present. Only the cell volts are measured continuously. Intermittently, people go around and dip things in there to measure the temperature. And they measure the weight of aluminum that they pull out of the cells periodically. But that's about it. Terribly low level of instrumentation. They consume significant amounts of energy. I've driven that point home, I'm sure. And the energy efficiency is only about 45%. So compared to what you need theoretically, thermodynamically, these are very inefficient. There are safety issues associated with wired instrumentation. Running wires around is very strictly forbidden. And in fact, anecdotally, I was at an aluminum plant yesterday in Tennessee and to test out some wireless instrumentation. And just before I was about to depart, the safety manager for the plant raced up to me in his truck, and he said, I just had a report that you used a tape measure in our plant. And he was absolutely irritated by it. And I had to promise him that I had not, in fact, done that. And the reason for that is a tape measure, of course, is metal, and it's long. And if you're not careful, you can touch something which is going to instantly electrocute you and could conceivably electrocute other people who might be in contact with other cells. So it's an absolute no-no to do that. And similarly, it's a great impediment to running wires around to measure things. Furthermore, there are a large number of cells per plant, a few hundred in a pot line, as they're called, and a large number of plants around the world. There's probably something of the order of about 100 of these aluminum plants in the world. And there's an opportunity for scavenging the energy to power sensors, as you'll see. And we're doing on time reasonably well. So, starting about 18 months ago, Mike Schneider, who I mentioned, took wireless devices to a plant called East Alco, just outside Baltimore, with these objectives: to test the concept of wirelessly monitoring cells. Would these strong magnetic fields produced by these 400,000 amperes interfere with the wireless devices? You cannot go into these plants, for example, wearing a pacemaker. That's absolutely forbidden because the field will stop your pacemaker or do something similarly obnoxious. You can't take watches or credit cards into these plants because they will get magnetized and damaged. So would that happen to a wireless mote? We wanted to monitor conditions in the duct from a cell, pressure measurement or temperature measurement to see if the cell cover is intact, that's that crust on the top of the electrolyte, and whether the cover panels are in place so as to minimize emissions. We wanted also to measure the heat flux from the shell of a cell. There's a steel lining, steel exterior to this cell, through which a lot of this waste heat flows, and the health of the cell is indicated by the magnitude of that flow of heat. So we measure that heat flux. That might be a nice diagnostic for the condition of the cell. And we also wanted to test the notion of powering wireless devices by energy scavenging rather than batteries. So if you imagine if you wanted to have, say, 4 or 5 wireless measurements on a cell, and there are a few hundred cells in a plant, then the task of going around and checking and replacing the batteries becomes an enormous one. So you want to avoid the use of the batteries in this context. So that was another important objective. What we've been working with is mostly these mode processor radios from Crossbow called Mica 2s, which are, I'm told, now starting to be old hat. There are better mode processor radios these days, but Mike worked with these and they proved very reliable, and we are continuing to use them to this day. I'll skip over some of the details of the thing there. This is what the hardware, one sort of hardware, looks like. This is for measuring temperature in a duct. So this is the business end of the device. So there's a thermistor here projecting about ½ an inch out of the end of the device. And this whole thing sticks into the duct. This here is a piece of a copper cylinder whose function is to take heat from the gases flowing past it and conduct it back here to where we have a thermoelectric generation device. That thermoelectric generation device has the task of powering the electronics over here. And of course, it relies on the existence of the temperature difference between one of its faces and the other. And with the way we do that is, first off, of course, having this conduction of heat from this copper rod here, but then having a so-called heat sink here, which is simply a bunch of fins which radiate heat into the surrounding air. So the thermistor is connected to this electronics here, and this electronics includes not just the Mica 2 mode, but a DC to DC converter to condition the power from the thermoelectric generator, and also a sensor board for taking the thermistor measurement and feeding it into the Mica 2. Here's a picture of what it actually looks like. There's the copper cylinder, the thermistor, the heat sink, and in the electronics. And this is a scale in inches to give you some idea of size. That's one kind of device for measuring gas temperature in a duct. We also created another device which is simply really a relay device. So it's a magnetically attached device, somewhat similar to the previous one, except it doesn't sense anything, so it doesn't have a thermistor. And the idea here is you clamp these things magnetically to the side of the cell. So you just pop them on there. Their attachment is therefore extremely quick, and you can move them around as you want to do so. And the hot side of the cell provides a hot side for the thermoelectric generation device, and then there's a heat sink on the other side. So you can use this device to generate power anywhere where we have a ferromagnetic hot surface. And that means that we can put motes more or less anywhere we want in the plant where we can find hot surfaces, and hot surfaces are common in these aluminum plants. There's no difficulty in finding these hot surfaces, and they can power motes which function as repeaters, as relays, taking signals from other parts of the plant and relaying them to a base station. So our campaigns at East Dalco started in early 2004. We measured duct pressure. That turned out to work, but was useless. The duct pressure measurement didn't contain any useful information useful to the operators or the supervisors. To our delight, the motes were undisturbed by the magnetic field and could communicate properly up to distances of about 100 feet. Now, in fact, in theory, these mode processor radios will go up to about 300 feet. But that's in open air in a field or something. In these plants, the buildings are of metal, and they contain these cells which have lots of aluminum and copper and things like that around them. So there's a lot of interference from metal equipment, overhead cranes and things like that. So the concern was, were we able to transmit a sufficient distance within the environment of one of these rooms, one of these big buildings? And yes, the answer was we could achieve 100 feet without too much difficulty. So that was an initial success. Later that year, we took moats that were powered with thermoelectric generators, like I've just shown you. We developed the DC to DC power conditioning for the thermoelectric generators, and then we did our first successful duct temperature measurements, and we magnetically attached moats as well. But I'm skipping over some of that old stuff to talk about the campaign that was a year ago, March of April 2005. We installed 11 moats and a laptop at East Alco for approximately 3 weeks. Four of those moats were powered by thermoelectric generation. We didn't do that to all of them because we wanted to save money. We had a relatively modest budget to work with. So the remaining moats were powered by batteries, which actually lasted for the whole 3 weeks anyway. We measured the heat flux from the shell and the gas temperature in the duct, and we transferred that data via the internet to Alcoa's Technical Center and to here at Berkeley. So here's where the moats were. This is looking down on the plant from above. So each of these is one of those big cells that I was referring to. So here's a line of cells. These are nodes which we scattered around, moats, and in this case this will be measuring a duct temperature and this will be measuring a duct temperature. I think that was a magnetically attached one and that was a magnetically attached one. And the receiving computer was over here in a trailer. I think there's about 100 feet between the trailer and this building, and these moats successfully communicated to the computer in the trailer. Everything worked perfectly until somebody came in one day to clean the trailer and unplugged the laptop and didn't plug it back in. So after about 3 weeks, we lost everything, but during the first 3 weeks, we were quite successful. So here's some representative data that came out of this investigation. This is for a particular day in a particular cell, this cell number on the 17th of April last year. There are two lots of data on here. One is the gas temperature in the duct, and the other is the heat flux from the cell. And let's start with the gas temperature. And that gas temperature should normally sit somewhere around 120 degrees Celsius. So you see it does for the first part of this day. Incidentally, this is actually 3 o'clock in the morning. So this is a time scale for the California time, and this is in Baltimore. So you have to add 3 hours to get clock time in Baltimore. So this is 3 a.m. This is 3 p.m. Okay. So in the middle of the night, these things operate 24 hours a day, 365 days a year, of course. In the middle of the night, there was a drop in temperature. And that drop in temperature was brought about by an anode change. I mentioned that the anodes need to be periodically changed. The way they do that is remove a couple of the panels. And if you remove a couple of panels, suddenly cold air is being sucked into the ventilation system and therefore into the duct, and the gas temperature drops. So that's a clear signal of the change of an anode. So what's remarkable about that? What's remarkable is how long that takes. Right? So normally an anode change is supposed to take about 10 minutes. And during that 10 minutes, excess gas is being sucked into the duct, which is bad news. It puts more of a strain on the gas cleaning system, for example. But it's supposed to take 10 minutes. But if you look at this thing, it's about an hour and a half. Well, what's happening? What's happening is the operators are cutting corners. So what they're supposed to do is go along to a particular cell, remove 2 of the panels, take the old anode out, put a fresh anode in, put the panels back on. Right? That's supposed to take about 10 minutes. What they would prefer to do, and what they were doing here, is they've got, say, 10 cells to change the anodes on. They take all the covers off those 10 cells. They take the covers off those 10 cells. Then they change the anodes on the first cell, change the anodes on the second cell, change the anodes on the third cell, so on. Then they go and put the panels back. All right? So during that time, of course, and that lasts about an hour if you're doing 10 cells, during that time, of course, there's excess air being drawn into the vent system and therefore the gas cleaning system, and it's not operating as efficiently. So, and you may notice that this happens at the dead of night, right? This is about 6 o'clock in the morning, 5 or 6 o'clock in the morning, when the supervisors are probably not there, or if they are, they're not being attentive. So this is operator malpractice, if you will. And if from this kind of temperature record, you can tell when it happens, right? And you can go and straighten the operators out, at least the following day. Okay, so that's one piece of information which is valuable to the supervisors and to the people who worry about emissions from this plant. Now look what happens. The temperature starts to creep up. And the temperature starts to creep up because when they change the anodes, they damage this pie crust on the top of the molten salt electrolyte. And they're supposed to clean that up, fix it by putting fresh alumina around the hole. If they don't, the temperature in the gas stream gets up because now there's hot molten fluoride electrolyte in close contact with the air which is passing up and the gases which are passing up into the vent system. So the temperature in the vent starts to creep up. And it's not supposed to go above about 130. And by the time we reach midday, it's well above 130, and all the way through till about, what would that be? That would be about 7 o'clock in the evening. It's high, okay? Indicative of the fact there's molten salt electrolyte now exposed to the air and excessive fluoride emissions. In fact, the environmental guy at the Alcoa Technical Center estimates that there's probably an order of magnitude more fluoride emissions here than there is here. So this is bad news. What happens? Well, around this time, somebody realizes there's a problem, right? And they go in and they take the panels off, so the temperature drops again, and they tend the pot. They close up some of these holes in the crust. So they put the panels back, the temperature comes back up, but it comes back up now to a reasonable value, at least for a while, and it starts going back up again. So you can tell a lot about the environmental emissions from this cell just by this sort of temperature record. And you tell a lot about what the operators are not doing that they should be doing. Let me glance briefly at this profile here. This is temperature, the heat flux from the shell, and you can see it drops in the middle of the day. This is 3 p.m. Right? Now this is April in Baltimore. It's well into spring. So what we're seeing here probably is a variation of the air temperature in the plant. The plant has open doorways. It's not heated or air conditioned. So there's substantial variation in the building itself. And that's probably what we're seeing there. That as the temperature of the air goes up, the heat flow from the outside the cells goes down. I got lots of other that kind of data. Here's another example. Temperature in the duct creeping up. Finally, somebody realizes something's wrong, goes on, takes the panels off, temperature drops, fixes things, puts the panels back, and the temperature behaves reasonably then for the rest of that day. Let me summarize all the data for 9 days, I think it is, in this plot here. So this looks almost like random noise, and these excursions that we see to lower temperature when the panels are taken off, and excursions to high temperature when the pot is poorly tended. This is the heat flux, and this is kind of interesting because you see there are 9 peaks and there are 9 days. So it reinforces the notion that what we're seeing is variation in the heat flux, which is due to variation in the room temperature, building temperature. The reason why I wanted to show you this data is because I want you to think about the task of going out and measuring the heat flux. Right? You quite clearly cannot go out and measure it once and have a number which is at all meaningful. You've got to go in and measure it over a significant period of time and do some sort of nice statistical averaging, or better still, some mathematical modeling to tell you what's going on with regard to that heat flux. Okay, so what are our conclusions from our past work? Well, we've demonstrated that wireless instrumentation of these pots works, and we've done that for a period of about 2 weeks. Wireless devices, the sensing modes and the relay nodes can be self-powered using thermoelectric generators. The gas temperature in the pot does carry signatures for correct or incorrect pot operation. And the heat fluxes from the pots are very far from steady state. They show a diurnal variation, probably due to variation in pot room temperature. And we need some statistical or modeling approach to give reliable results. So what's in the future? Well, what we'd like to do is complete instrumentation of an aluminum smelter and measure not just the duct temperature, but heat fluxes, the distribution of current amongst the various anodes. All kinds of other parameters can be measured fairly conveniently and not very expensively by the implementation of a wireless approach. We'd also like to extend this technology to similar plants. So there are lots of other things which are made by electrochemistry, by electrolytic processes, besides aluminum. They don't consume quite as much energy, but they still consume significant amounts of energy. And some of them have emission problems. So the similar plants are copper plants, zinc plants, magnesium plants, and things called chloralkali plants. Chloralkali plants are ones that make chlorine and sodium hydroxide. And that's quite a big industry. So they're in a sense somewhat similar to aluminum. They're electrolytic and so on. But we could go to other industries, for example, paper making. Turns out that the aluminum industry is not the worst offender when it comes to electrical energy consumption in this country. The worst offender is paper making, which I had not realized until I looked at those energy information administration statistics, that there's more electrical energy consumed in this country, at least, in making paper than in making aluminum.
So what's the efficiency there?
I have no idea.
Sorry.
And I'm not even, well, actually, I'm not sure that you can define an efficiency in that context in the same way you could do it. It's different, yeah. Weaving is another possibility. Petrochemicals, da-da-da-da-da. And when is the technology best applied? When is wireless technology best applied? First off, when there are many small units, but small in inverted commas, because obviously these electrolytic cells are not small. They're not desktop devices. But the production of aluminum, as you can see, is in a typical smelter, is carried out in a few hundred units. This is rather different from the way we make steel, for example, where a steel plant has one or two big blast furnaces and one or two basic oxygen furnaces, and that's it. Aluminum plants have all these little units, hundreds of them. It's best also, of course, when the production is inefficient in some way. Energy inefficiency in the case of the aluminum industry. But you can think in terms of other inefficiencies, for example, in weaving. If you're constantly breaking the thread, if you're weaving, then that's an inefficiency. Okay. Where instrumentation is presently lacking but would be valuable. There's no point in trying to instrument things where the values you measure are not going to be helpful in terms of improving or running the technology. Where there's cost or safety aspects of the technology which inhibit the use of wired sensors. Right? There's wireless we think of as being quite inexpensive, but there are some circumstances where it's actually cheaper to run a wire. But fortunately for us, the aluminum industry is not one of those circumstances. And where, of course, there's opportunity for energy scavenging, because if you're going to apply this technology where you have hundreds and hundreds of modes in a plant, you certainly don't want to have people whose responsibility is to go around and change the batteries. Because you can't afford those people. People are extremely expensive, at least in the United States. So that's our vision of the future, and is my last slide. And I thank you for spending your lunchtime here, and I'm happy to entertain any questions.
Very nice. A few questions from the floor?
Go ahead.
Yeah. Please clarify why you say many small units and not if there are a few large units?
Well, let me make the comparison with steel making. Whereas I mentioned what you have in a typical steel plant is one or two huge units called blast furnaces, which take iron ore and make iron out of it. And then 3 or 4 small units which take that iron and make it into steel, and they're called BOFs for short. Typically, even in some of the outdated steel plants we have here in the United States, the instrumentation on those devices is really quite advanced. So that, for example, it's not unusual to have television cameras mounted inside the top of a blast furnace so that the operators can see the way that the stuff you feed in the top is distributed inside the furnace. So if you've got a few big units, then it's not very difficult to justify some fairly expensive and extensive instrumentation on it. But if you've got a lot of little units, little in the sense that there are lots of them needed for your production, then it becomes a different matter. You can't think in terms of spending tens or hundreds of thousands of dollars on each of those units, whereas you could do in the case of a blast furnace or a BOF.
Question in the back first.
I was just curious about your opportunities for energy scavenging. What kind of opportunities are particularly open for energy scavenging?
Well,
how big, like thermal gradient, that sort of thing?
okay, Paul should answer these questions, but let me make a stab at it to start with. It's not hard to achieve a temperature difference of, say, 50 to 100 degrees Celsius, which is easily enough to, well, depending upon the size of the thermoelectric device you're willing to buy, that's easily enough to generate enough power to run these devices. But thermal energy scavenging is just one aspect of one possibility. So that if I turn to weaving, for example, the mechanical energy scavenging might be better. And Paul.
Well, yeah, just quickly. I mean, there's a lot in some of the weaving applications. There would be very large vibrations that you could use. In the petrochemical plant, there might be a hybrid set of situations where the outside of the plant could be open to the sun, so you could scavenge power. From solar point of view, externally, a little more internally, there might be places where there's heat differences which you could use, and then again there might be some vibrating equipment.
Pumps and things, yeah.
Foster Miller is another company that approached us recently, running a prototype inside a submarine, and there's another highly vibrating environment. And our buddies at Telos, Motive rather, they did run a little prototype with Rockwell and British Petroleum, I think, where they put some modes inside the hold of a big ocean-going liner, and they were using the vibrations. All these have been prototype applications so far, but those are three: solar vibration and heat seem to be the most attractive ones so far.
So for the vibration, do you need a particular frequency that has to be regular or periodic, or can it be abnormal and unpredictable?
There's a long answer to that question.
Well, I won't take you here.
Okay, we could talk offline, but the short answer is that the ideal situation is where the device is designed to resonate at the frequency of the surface upon which it's being mounted. But and continuous vibrations are better. But still trying to keep the answer short, if you tailor that to what the duty cycle will be, it's not a disaster if it's not continuous. And secondly, another one of our students, Eli Leyland, did investigate the possibility of just tuning the device to suit frequency. So you measure the frequency of the surface. He built this little device that compresses a piezoelectric device. It's like the opposite of a guitar string. You're compressing it to change its natural frequency. And so you tweak around a little bit at the beginning and adjust the behavior of your device to suit the surface upon which it's going to be mounted. So that's probably about as much as I should say right now. But we can talk about that. Yeah. Jim, sorry, back to you.
No, there's another question. Go ahead.
I've got a whole host of questions, and answer the ones you want. What's the alkaline metal that's combines with the fluoride? Are the covers and the pots insulated? Can you use the thermoelectric device itself, the voltage coming from that, as a crude measurement of the temperature, and therefore forget the thermistor?
Yeah.
Let's see. And then can you go to the basic process itself and combine electrolytic conversion with thermal conversion from oxidation reduction of carbon?
Okay. Gee, those are many questions. Let me attempt answers to one or two of them. I suppose you could use the output from the thermoelectric generation as a measure of temperature. I don't think that would be all that precise, however, because it would be a function of the temperature on the outside.
Which is easy to measure.
Well, except, this is a plant where the doors are open, there are winds blowing in, and there are hot things nearby making this area hot and this area cold. So I'm not... the thermistor is not expensive, and they make good measures. The cells are partially insulated, as it turns out. The panels on the top, incidentally, are not. They're just pieces of aluminum. The cells themselves are partially insulated to control the heat losses, but it turns out you can't completely eliminate them. And I can't explain that in anything less than about 5 minutes, so I won't attempt to do so. You mentioned using thermal energy. There's at one extreme there is some technology that is being worked on, has been worked on for about a century now, and is still being worked on by Alcoa, called carbothermic reduction, where you run a sort of blast furnace where you reduce aluminum oxide, which is where the aluminum comes from, using carbon, using coke. And that may eventually come to fruition, but it hasn't done so far. But what does happen, however, is the consumption of the carbon in these cells lowers the thermodynamic potential you need to produce aluminum from aluminum oxide. If you had an electrode which was generating oxygen, for example, rather than carbon dioxide, then the cell voltage will be higher. Although there is a lot of work on that area as well, because the aluminum industry is quite naturally apprehensive about restrictions on CO2 emissions, and therefore is devoting a lot of attention to the possibility of an alternative anode, a so-called inert anode, which would generate oxygen rather than carbon dioxide. Did I answer most of your questions?
What's the alkali metal in the electrolyte?
Oh, the electrolyte is loosely cryolite, sodium aluminum fluoride, but it's got a few additions in there. In sodium aluminum fluoride, it's Na3AlF6, so the ratio of sodium to aluminum is 3:1. And it's not quite that ratio. It's adjusted to be somewhat different. And then they add things like magnesium chloride, and some folks put lithium chloride. It's a bit of a witch's brew.
Shakespearean ending.
Right.
Let's wrap it up at that point, I think, with another round of applause for Professor